Good morning, everyone, and welcome to this lecture. This is lecture number 5, and we are dealing with magnetic effects of current. In the previous class, we had seen the magnetic field due to a circular loop. We had seen how we can find a magnetic field due to a circular loop, and if it is not a loop, if it is a part of the loop, how we can find out the magnetic field. We had also seen the simple questions, not simple questions, questions which are more likely to come, and we had solved all of these questions. The most important aspect in all the questions that we solved would be to find out the direction of magnetic field. If you get the direction of magnetic field correctly, you should be doing well. And these important cases where the magnetic field happens to be zero because they cancel each other out, this is what you must remember. Do we understand this? Yes or no? Do we recollect this, what we had done in the previous class?
Yes, sir.
Okay. Let us begin today's class. Let me see. We begin today's class with something which is known as your Ampere's law. What is this Ampere's law or Ampere's circuital law? So we will start with this Ampere's law or Ampere's circuital law. Ampere's circuital law or Ampere's loop law or whatever you call it. Now, suppose you have a loop and you have some current carrying wires coming in that loop. So, this is the diagram that we can have. Suppose you have a lot of current carrying wires. You can see some current carrying wires like I1, I2, and I3. Then there are some more I4 and I5. And what we are doing here is we are creating a loop. Now all these wires are going to create magnetic field in this closed loop that I have created, and you can see this closed loop which is shown by this yellow thing. I have created a closed loop, and in this closed loop there are some wires which are coming in this loop. There are some wires which are outside of this loop. Ampere law basically tells us, and if I give you the statement of Ampere's law, if I give you the statement of Ampere's law, the line integral of a magnetic field over a closed loop, the line integral of magnetic field over a closed loop gives us, is given by mu naught multiplied by the current in that loop. Now, this might look very difficult while you are writing it, but if you write it in the correct form, in the form of integral, so it is this line integral of magnetic field B dot dl, the line integral of magnetic field over any closed loop is mu naught times current enclosed by the loop. This statement is known as Ampere's circuital law. And this circuital law, Ampere's circuital law, looks like something that we had already seen. The surface integral of electric field was charge enclosed divided by epsilon naught. If you recollect, this was Gauss law. Do we remember this was Gauss law? This was Gauss law And the one that I have written is known as Ampere circuital law. Now remember, in this Ampere circuital law, we only include the current which is coming inside the loop. In this loop, we are having three currents. Do we see those three currents? Yes or no?
Yes, sir.
Those three currents are I1, I2, and I3. And I am moving in the loop in this direction. As you can see, my direction is anti-clockwise. So I am moving in anti-clockwise direction. Anti-clockwise direction. The thumb represents positive direction, and other current will be taken as negative. So here I1 and I2 current will be I1 and I3 current, because I'm moving in the anti-clockwise sense. I1 and I3 current will be taken as positive, and I2 current would be taken as negative. So if I write the Ampere circuital law for this circuit that I have created, it will be mu naught into I1 plus I3 minus I2. Do we understand this? Do we understand this?
Yes, sir.
This is how we write Ampere circuital law. This is just a concept. I'll give you one or two questions, and that is enough for you to understand here. There is nothing much that we can do over here. So this is Ampere circuital law. You must remember that the current that we have in this law is the current which is enclosed by the loop, and the current which is coming outside of the loop is not taken into this equation. Do we understand this? Do we understand this?
Yes, sir.
Okay, I'll give you 2 minutes to note this down. Let me know once you are done. So this is Ampere circuital law. It's a simple law. And now I'll give you a couple of questions based on this, and I hope you will be able to solve those questions. This is the first question that is going to come on your screens. You have to find out the line integral for the loops that I have given. There are three loops that I have drawn, and then there are four or five currents. You have to find out the integral of b dot dl for all the three loops, and I'll give you 1 minute, 2 minutes to solve it, get the answer, and get confident. So how are we
And
supposed to do this? It's very simple. Let us first concentrate on this loop. This loop is L1. I'll do it for this loop, and then I'll hope that you can do it for the other loops. B dot dl, the integral of B dot dl for this pink loop. Remember, the current is like this, like this. So whatever is going up is positive, whatever is going inside down is negative. I1 is moving up, I2 is moving down. So it will be equal to mu naught into I1 minus I2. That will be the integral of B dot dl for the pink loop. Do we understand this?
sir, L3, no current is passing through it, no, sir.
Yes, L3 no current is passing. Then I have this loop, the green loop. In this green loop, we have three currents which are enclosed. So integral of B dot dl for this green loop. Again, the loop is like this. So up currents are positive and down currents are negative. Up currents are I1 and I4. Down current is I2. So that is the integral of B dot dl for this one. In the blue loop, there is nothing coming in this blue loop. So integral of B dot dl in this blue loop is nothing but 0. Do we understand this? Yes or no? No, yes. This is
Yes,
as
sir.
simple as it gets. This is as simple as it gets. And anyone got this answer? Yes or no?
Yes, sir.
Okay. Now you must remember some more important points about this. So we move on and you just mention important points. We have written some points and you can write more important points. Remember from these important points, you may have a question coming up in your paper. So the first important point that we are going to see is this one. Line integral is independent of the shape and the position of wire. Any shape wire, any shape loop, position of any wire, it does not depend on it. We did not see what was the position of the wire. The only thing we saw was whether the wire was coming inside the loop or it was coming outside the loop. Do we understand this? Yes or no?
Yes, sir.
The integral of B dot dl is 0. It does not mean that B is 0. If B is 0, obviously it will be 0. But if it is 0, it does not mean that the B is 0. It only means that there is no net current which is passing through the loop. Do we understand this? Do we understand this?
Yes, sir.
Then the direction of current, I have already told you. The direction of current depends on the direction of loop. In whatever direction you are moving, you turn your fingers. This is how it is written. The current due to B is produced in the same sense as DL. Direction will be taken as positive depending on the sense of rotation. Do we understand this? Yes or no? I'll give
Yes,
you
sir.
a minute to note it down. Then we can move on and see what are the applications of this Ampere circuital law. And we will just write them and write their formulas. Application of Ampere's law. Now this Ampere's law can be used to find out magnetic field due to infinite wires or infinite cylinders or infinite solenoids. So we will go through them one by one. Number one, magnetic field due to infinite wire. We'll go through it again. We have already seen what is the magnetic field due to an infinite wire. Do we remember? Magnetic field due to an infinite wire. Anyone can tell me the formula? What is the magnetic field due to an infinite wire, bacha? What is the magnetic field due to an infinite wire at any point?
Mu naught I by 2 pi r.
U naught I by 2 pi r. That is correct. Up till now, what we were assuming that the wire is kept like this. So magnetic field at point P was mu naught I by 2 pi r. But I told you that the magnetic field is moving in circles. Yes or no?
Yes, sir.
Now we can look at the same wire in a different way. You can look at the same wire in a different way if you look from the top view we call it, top view. Top view means, see, if this is a wire like this is a wire like this, it is having current in this direction, wire is like this, current is in this direction. If you look from here, you can see magnetic field moving like this. Yes or no? I'm looking from here, I will see current like this and magnetic field moving like this. The same thing if I look from the top. If you look from the top, it looks like this. The current is going like this. Yes or no? So you will see that point dot. The current is coming like this, and then the magnetic field will move like this. Do you understand what I'm saying? Magnetic field will move like this. Are you getting what I'm saying here? That is known
Yes, sir.
as the
Yes,
top.
sir.
From the top. And that is the view that I am going to show now in this. That is the top view of the same wire that is on the left hand side. Do we understand this? The top view of the same wire that is on the left hand side. Do we understand this? Yes or no? So the current is now coming out, and you can see this point P actually comes here, and you can see the magnetic field is moving in a circle. So at point P, the magnetic field is going up. At point Q, the magnetic field, same magnitude, but direction has changed. It is going like this. At point R, same magnitude because the distance is same, but it's going down. At point S, same magnitude, but the direction has changed. It is going towards right. So you put your thumb in the direction of current and you can see the magnetic field moving in circles. We understand this. We understand this. Yes.
Yes, sir.
At all the points, magnetic field is going to be same. I can prove this by your Ampere circuital law. Remember, Ampere circuital law is B dot dl. The integral is mu naught. The only current in this is I. B dot is integral of dl is nothing but the circumference of the circle 2 pi r. Do we understand this?
Yes, sir.
So we get the answer as B will be equal to mu naught I by 2 pi r. Everyone understands the application of Ampere's law? Mu naught I by 2 pi r. This is the magnetic field due to an infinite wire. I'll give you a minute to draw the diagrams and let me know if you have understood this.
Yes, sir.
Then the next sort of question that can come to you, magnetic field due to, just give me a minute. Magnetic field, case number 2. Magnetic field due to infinite hollow cylinder. The cylinder is infinite, but it is hollow. It is hollow, it means it only has current on its surface. It is hollow, it means it only has current on its surface. Do we understand this? The radius of this cylinder is R, capital R. Inside, if you look at this green loop, inside there will be no magnetic field because there is no current. Yes or no? Yes or no, my dear friends? The current is only on the surface. Otherwise, it is hollow or empty.
Yes, sir.
Yes,
So,
sir.
the magnetic field inside the magnetic field is going to be a zero, 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 zero. Then you have a point P on the surface, my dear friend, on the surface, my dear friend, it is mu naught I by 2 pi r. And remember, this is the maximum magnetic field, and the maximum magnetic field happens to be on the surface of this. Magnetic field is maximum on the surface of this. If you take any point outside, if you take any point outside at a distance r, if you take any point outside at a distance r, please listen to me, then write, then that will have full current enclosed If it has full current enclosed, the formula will be same as that of a wire, and the answer will become mu naught I by 2 pi into small r. So outside the formula is same, inside the formula is 0. On the surface it is maximum and the value is mu naught I by 2 pi into capital R. Here is a small graph. Here is a small graph that tells us the variation of magnetic field with the distance from the center or the axis as a function of x. You can see inside, inside is the region of green. This is the inside region, and you can see the magnetic field is 0. Do we understand this? The inside region magnetic field is 0. This point is the surface wala point, and you can see at this point the magnetic field is maximum mu naught I by 2 pi r. Outside the magnetic field at everywhere is in the yellow. Oh, why I'm getting yellow? Magnetic field is in the blue range. That blue thing is for outside, and outside everywhere the magnetic field is mu naught I by 2 pi small r. Have you understood this? Yes or no? No, yes.
Yes,
Inside
sir.
field is 0. Please remember, it's a very important graph. I'll give you 2 minutes to note it down. This was an infinite hollow cylinder. The next one is it will not remain hollow. So now I have the third one, infinite solid cylinder. Now, if I have an infinite solid cylinder beta, then it will have current which is coming inside as well. Yes or no? It will have current
Yes, sir.
which is coming out inside as well as outside. So magnetic field will not be 0 inside also. So if I just show you the diagram here, if I just show you the diagram here, the cross section area will be looking like this. It will have current coming inside as well as current coming in the outer surface. So again, if I show you the top view, this is the top view of the same thing. This is the top view of the same thing. I could not make it big because let me make this one small then. Okay, now it looks better. So you can see it's a solid cylinder now. Magnetic field will exist inside. The inside loop is this green loop. Do you see this inside loop, green loop? Magnetic field inside is not now 0. The magnetic field inside will be given by this formula, mu naught into I into small r divided by 2 pi into r square. Inside, the magnetic field is directly proportional to r. A very important result that you should remember. If you look at the point on the surface, this is the surface loop that I have created on the surface. Magnetic field on the surface will be same. Magnetic field on the surface will be same as mu naught I by 2 pi into capital R. This is the maximum magnetic field. If I go outside this one, the blue one, the magnetic field outside, the magnetic field outside, the formula is same as that we had done in the previous case, my dear friends. The formula would be same. If you draw a graph, bacha, draw a graph between magnetic field and the distance from the center. This is how the graph would look like. As you can imagine, the graph inside would be a straight line because it is directly proportional. So that I will draw as the green thing. In the green thing, it is inside. So magnetic field is directly proportional to R. Do we understand this? In the green region, this is the surface point, and surface point you have magnetic field as maximum, and then this is the outside points, the blue points. Magnetic field is inversely proportional to R. Do we get this, bacha? Everyone? Yes or no?
Yes, sir.
We give you 2 minutes to note this down. Let us move around and I shall give you this one. Now, different cases, I will put them together. We have seen the two cases. Now, these are all the cases. One more case is left where we have a thick shell. So I'm putting all those in one thing here. Uh, Let me just try and put. I think. Just give me a minute. Okay. These are all the cases put together for the wire or the cylinder. Remember, all the wires or all the cylinders are infinite in length. In the first case, we are looking at a magnetic field outside the cylinder. In all these cases, whether it's a solid or a thin hollow or a thick hollow cylinder, outside field for every one of these is mu naught I by 2 pi r, small r is the distance. On the surface, the magnetic field is mu naught I by 2 pi r. Do we understand this? On the surface means on the outer surface. Do we understand this? Yes or no?
Yes, sir.
We talk about inside this. Inside the solid cylinder, magnetic field is not zero. We have seen the formula. Yes or no?
Yes, sir.
Inside the hollow cylinder, it is zero. We have seen that? Yes or no?
Yes,
Inside the
sir.
third one, in this vacant space, magnetic field is zero, but in between the magnetic field is not zero. We will see the formula of this in the next class, that is tomorrow. Right now, I would request you to draw all these diagrams so that you have a very clear picture of what we are up to. I'll give you 2 minutes to do this. So once you have
I'm
done,
not completed, sir.
we are finished with the class for today, and I'll keep this screen on till you have noted it down. We're done for this class, and I hope you remember these results when we meet in the next class, because we'll be doing a couple of problems and we'll be winding this topic, the magnetic force, by tomorrow's class. Remember these things. One of these questions is going to land up in your paper. Take care. God bless all of you. Bye bye.